Right, welcome back. Is everybody recovered from lunch? Had 2 coffees? Anyway, next up, we have Mr. McVittie, who is going to talk to us, I guess this time on cross-compiling again.
Yes.
So, Simon, over to you, sir.
Hello. Who is this? Ugh, my remote's not working. Where? Right, better. Sorry. Yes. For those who don't know me, I'm an engineer, software engineer at Collabora. So we do consulting on various open source and open source adjacent projects. But more importantly for this talk, I'm also a Debian developer in a bunch of teams, including the GNOME team. And GObject-Introspection is something we use quite a bit in GNOME. The desktop wouldn't work without it. So the big idea of this is some years ago we used to have the idea that you would have one binding for each C library for each language, and that was great when it worked, but it really didn't scale. So in practice we ended up with one Python bindings for everything, Perl bindings for half of it, JavaScript bindings for none of it. So the idea is instead you can generate a description of your API, which is the introspection, and you can write one binding per language that's generic for all introspected libraries, and then you get every binding for every library without having to do the full cross-product of everything you need. So this works for dynamic languages like Python, Perl, JavaScript, where you're creating the bindings as you go. It works for static languages like Rust, where you're generating source code and compiling it. And the lower levels of this are now integrated into glib, which is the most basic library in the GNOME world, so that you can rely on having them everywhere. And the reason this works is there's a set of conventions that are used in GNOME and GNOME-related libraries, this thing called GObject, which originated as the bottom layer of GTK. And it's an object-oriented system, vaguely similar to Java, I guess, but done in C. So it does the usual pseudo object orientation with callbacks and vtables. You can have first-class citizen objects with classes. You could also have boxed types, which is when you have things like a hash table that is not worth making it a full object, but you need to know how to copy it, how to free it to write a language binding. And then there are these unique things that are not in most object-oriented systems, signals and properties. Qt also has these because they are something you really want in a graphical user interface. So you can have an event happen, like button is clicked, and other parts of your program connect to it without having to have an explicit dependency. So to get this into language bindings, we end up with 2 different formats. The first one is a description of the API, so what you write your source code against, which is in XML. It's human readable, which is sometimes useful to check that your bindings have come out correctly. It's human writable if you have to, but please don't. It's usually architecture independent. There are exceptions, I'll come to that. And it's done in terms of the abstract types that you would normally deal with. So for instance, size t or time t are what you would expect to find in that. And then there is also the type-lib, which is an efficient binary format that the XML gets compiled into, because you don't want to be parsing XML every time you start up a Python program. So this is a dense binary format, not designed to be written by hand, not designed to be read by hand. It's basically structs on disk. And this is what you use for your dynamic languages. And unlike the XML, this works in terms of concrete types. So it's not your size of your G variant in this case is not a size T anymore. It's a uint64T if you're on a 64-bit platform. Size may vary, which is one of the reasons that this has to be compiled once per architecture for this architecture's definitions of what size is everything. So we have this quite simple pipeline where it parses the source code to find out what's in your library, reads all your declarations. There's a program called GIR scanner which does that. You get the XML, you run that through a compiler for each architecture, and you get a type-lib, which you can use in your Python programs. All nice and simple, and not, in fact, true. So the problem is GObject has runtime type information. So things like the signals, or what your superclass is, or what properties you have, you register these during program initialization by writing code, which is nearly always the same for every architecture. But if you want to, please don't, you can do something like this and have a property that you create imperatively at runtime with different types depending on what environment you find yourself in. And like, you could go even worse than this, and instead of being based on, this is something you could do with compile type conditionals, but you don't actually have to. You could have a timestamp that is an int64 but only on Tuesdays. This would be very silly, but it is technically possible. So, if my remote works, yes, please don't do this. So what actually happens is the introspection happens when you are compiling the library you're introspecting. This is where the word introspection comes from in this. So you compile your library into a shared object, and one of the things that GIR scanner does is it generates a little executable called the dumper, which produces a machine-readable summary of all the signals, all the properties, some other stuff like error domains. And that ends up in your XML as well, which is necessary to have a full representation of what your object looks like. And this all becomes a bit awkward if you're cross-compiling, because when you're cross-compiling, you have your build machine, typically an x86 PC, anything fast or convenient for you to use. You want binaries for a totally different architecture, so in deference to ARM kindly hosting us here, I'm going to assume you're targeting ARM, but it could be anything. And I am going to be using the terms in this talk that Dpackage, Autotools, and Meson all agree with, where you have the build machine and the host machine. But some cross-compiling toolchains, just to confuse you, use different definitions for these terms. So if you're using CMake, you will need to substitute terms accordingly.
Don't read the GCC manual, your brain will leak out your ears.
And, okay, yes, if you want to be really confused, read the GCC manual. So, I mentioned that type libs have concrete type sizes in, so you get a different type lib on 32 and 64-bit platforms, typically. So you need an architecture-specific compiler that knows the right sizes and will produce the right output. In principle, we know how to do this. There's a common convention that if you're cross-compiling for example, ARM, you put the GNU tuple at the beginning of your executable name, and you use that specially named compiler. It's what you'd do for GCC, and you can do exactly the same thing for the typelib compiler in principle. The hard part is when you're scanning the library and you're doing introspection, you need to run host architecture code, the dumper executable, because if you ran code from your build architecture, you'd get the wrong answers. So you're running on an x86, you've got ARM code, now you want to run it, how do you do that? And just to make things more confusing, the search paths are different. I mentioned that the XML is usually architecture independent. The problem is, because it's a description of the API, it includes things like, here are some macros from my library that are constants that you use to access stuff from this library, which can include things like a constant representing the current endianness, and obviously that's going to be different if you're on a little endian PC or if you're on a big endian S390. And there's only a couple of libraries in Debian that are known to have this problem. GStreamer has some endianness stuff, and unfortunately the other one with this problem is glib, which is at the bottom of the stack and everything has to use it. And because of its position at the bottom of the stack, it cares about endianness, it cares about printf formats and things. So we have to look in a different place to find the right XML to describe the right architecture. So if we want to cross-compile this stuff, there is an easy approach to getting 90% of what you want in 10% of the effort, which is maybe don't. So, some time ago, we invented this build profile. Build profiles are great. They're a way of turning off parts of your package that are not relevant. So, building a thing without the GUI or that sort of concept. And we've defined a build profile, no GIR, which means don't build this stuff. Ideally, if you're using a build profile, you want to turn off entire binary packages so that you're not changing the interface of anything. So there is this conventional name for the bindings for the foo library. And if you can just not build that binary package, then great. Similarly, if you package the XML describing the library, the easy case is you have it in a separate dev package, which is a convention we've started using. And if you do that, again, you could just not build that package, and the contents of the main dev package that C programmers use will remain the same. If you can't do that because you don't have this separate package and you don't want to go through the new queue to add it, then you have to start dropping bits of your package. And obviously that's an API break. You used to provide a feature, now you don't. That's awkward. But we do have mechanisms for dealing with that by making your dependencies like opt in to I want this bit as well by using a virtual package. And similarly, Vala bindings. Vala is a weird GNOME-specific language that is like the syntax of C#, but transpiled to C, which was very popular for a few years and is still around in some programs. And the tradition for this is you put your bindings in your main dev package and you generate them ideally from the GIR XML to avoid duplication of effort. And so these are something else that if you're not building the introspection bindings, you're going to have to drop those. And again, you're losing a feature you previously had. So this is an API break, so be careful. So we can compensate for those API breaks. So we've invented a conventional name for the XML describing an API, again, based on the API's namespace name and version. So you can have your dev package put this in its provides, and then go around updating all your consumers to depend on that if they are building their GObject-Introspection bindings. So if your library is something like libflatpak, which is used by like 2 other programs, this is great. It's very easy. You can just go and change GNOME software and KDE equivalent, and then come back to libflatpak and drop the bindings, and it's easy. If you're maintaining something like GTK that the world and his dog depend on, then you're going to have to go around quite a lot of consumers of that API to be able to do this safely. But eventually, you've fixed all the dependent packages, and now you can build with the no-GIR profile if you don't want that bit. And the introspection tools that we have in Debian automatically make this provides expand to be empty if you're not building the relevant bits. So a consumer of your library can tell whether it's the full one or just the partial one by whether it has this provides or not. And if you want to, you can go through the new queue, add a separate binary package, and do it sort of properly at the cost of waiting for review. So you might reasonably say, Simon, you said you were going to talk about cross-compiling. We haven't talked about cross-compiling. What's going on? So we now need a mechanism for actually cross-compiling this stuff. And clearly the answer, if we can't get away with not doing it at all, is cheat. We have QEMU. It's basically magic. It can run programs from another architecture maybe we can use that. So the scanner, to make this work, we had to look at how the scanner actually works. The vast majority of it is written in Python and is just parsing source code and finding your declarations. That part is quite easy. And ideally, we want to be not emulating all of Python, because that would be really slow, and that way lies madness. It also loads a little C extension to load the GI repository library to get some of the implementation details of how this stuff works behind the scenes. And unfortunately, if we're going to run the build architecture's Python, we're going to need the build architecture's copy of that C extension. Otherwise, it won't load. So we have to be a bit careful with that. And then it compiles and runs this little C program, the dumper, so that it can get information about the stuff that is actually introspected at runtime. This is a lot smaller. It depends on glib and nothing else, and the library you're introspecting, but nothing else. So that's a lot more reasonable to emulate. It also, unfortunately, runs LDD on your library to find out what you depend on, and screen scrapes the output, which is not great. So, if we want to do that better, we want to use the Python code as is, because we don't want to run an entire host architecture Python. And you need the build architecture Python anyway if your build system is something like Meson, which hopefully it is. We can change the search path to use the host lib directory, directory to find the XML before looking at the build architectures directory. That's fine. We can run the dumper binary via QEMU user. All it does is memory allocation and a little bit of I/O, so it doesn't do anything complicated. It doesn't do anything slow. That's easy. And LDD, not actually a great idea. But every platform we care about in Debian uses ELF. And you can parse another architecture's ELF header without needing to know anything about the architecture you're looking at. So I wrote a little program that uses libelf and outputs a list of dependencies in the obvious way, which also avoids having to screen scrape output that was designed to be human readable. This is actually something that I want to eventually get upstream, because using LDD is just not the right answer. But that's not quite there yet. But I did send some fixes upstream to make it stop assuming that it was seeing recursive dependencies. So there's preparation work for that gone upstream. And so we have this wrapper script in the end, which runs the normal Python GIR scanner, but passes it a bunch of options to tell it to use these substitutes for what it would normally do. And it uses the cross-architecture prefix, so it fits your normal convention. We also need the compiler. Going back to my flowchart, we've done the scanning so far. We need to compile the typelib. And the classical like C compiler way of doing this, as Ian alluded to, would be build it once for each pair of build architecture and host architecture. And we've got currently 9 release architectures, 9 Linux ports that have a build D, 2 ports with build Ds and not even a Linux kernel. I don't know how many non-build D ports that theoretically exist. We need to know information about each of these architectures. That's quite a lot of work, and to make it worse, upstream is not going to be interested in this, because their attitude to cross-compiling this stuff is, why would you? So let's not go that way. Just so happens, GIR compiler is actually quite simple. All it does, basically, is allocate memory and write files. So if we run it under QEMU, it's not actually that bad. The problem with running things under QEMU is it's often slow, and obscure or advanced syscalls might be a bit wrong. But neither is true here. Like, it takes seconds at most for a big build. So if it takes maybe a minute for a very huge build under QEMU, nobody will know. Similarly, it doesn't do any fancy syscalls, it just does I/O. So we have a similar wrapper script for the GIR compiler, which runs the right one. This doesn't actually need to override the search path because we are literally running the ARM version or whatever. So we don't need all the special options we did for the scanner. There are a bunch of other tools, but they are all kind of the same shape as one of the ones I've talked about. So there's a tool for documentation, which is like the scanner, but different. There's versions of these tools that have ended up in glib itself as part of making this a bit less siloed and a bit more integrated into the whole ecosystem. But they behave the same as the one in the separate GObject-Introspection project. There's a decompiler that takes your type libs back to XML with some information loss. I don't know why that exists, to be honest, possibly just for debugging. Some people insist on running it, but they probably shouldn't. But it's the same shape as the compiler, so we can just do the same answer, and it works for all of this. So that's simple enough. But to get any of this to be run, you're going to need to fix the build system of your package. Otherwise, your build will just try and end up run the build architecture's GI tools against a library that was built for the host architecture, and it will be very sad. So auto tools, everyone's favorite build system to hate. This is actually quite straightforward. So AutoTools has this distinction between checking for a program that is just a program, which is how you look for something like sed or dbus daemon or curl or something, or checking for a tool where the difference is for a tool, it will look for the architecture prefixed version first. So if you're cross-compiling for ARM on your x86 PC, it will look for the special ARM GIR compiler. And conveniently, the macros that are supplied with GNOME's GI toolchain already do this. They already look for the cross-prefixed version. Nobody else, as far as I know, except Debian, provides the cross-prefixed version. But as soon as we do, the right thing happens. So, great. Meson, which GNOME has been using as a replacement for AutoTools, on the basis that AutoTools is looking increasingly creaky. The way you do cross anything in Meson is you give it what's called a cross file, which is a description of your cross toolchain in roughly ini file format. You could also, in a native build, give it a native file, which is the same format but with slightly different contents, and that it tells you if you think you should be using this tool, use that tool instead. So in the packaging for the GI tools in Debian, we have supplied a Meson cross file for the host architecture. So you can just set up your Meson arguments in your package's build system to use the right cross file. It contains the right cross tools. Everyone is happy. There is this thing debcrossgen, which is run by debhelper if your build system is Meson, which is how it knows to use the right cross GCC and linker and all that kind of thing. And in future, hopefully debcrossgen will learn about this, and so instead of explicitly specifying this file, you'll just be able to say, it's a cross build, you know this, and the right thing will happen. Unfortunately, debcrossgen is Debian specific and unmaintained, and its maintainer is very unhappy about it. So, Meson upstream has this thing called env2m file, which generates machine files from your build environment. And this is the replacement for debcrossgen that hopefully we can teach that to know to find the right tools so that your project will do the right thing. CMake, another popular build system. GNOME doesn't use this very much. I think Evolution uses it. but lots of non-GNOME software does it, which might be using GI as well. We don't actually know how this works. So if you know how to make this work, the GObject-Introspection package would like to have merge requests for readme.debian to tell maintainers of dependent packages what they ought to be doing here. I suspect it's kind of similar to Meson, that you need to write some sort of toolchain file and tell your build to use it, but we don't know at the moment what that file should say. If you like to do everything from first principles, you might use not AutoTools, not Meson, not CMake, but your own secret fourth thing. And there is a pretty strong convention in these that if they've been updated by people who care about cross-compiling, they will have this variable cross-compile, which is the prefix to put on all your tools. So you see this in the Linux kernel, for example. And normally it expands to empty, and you get the default GCC, the default GAR compiler, and so on. But if you have put this prefix on all your cross tools, and you run it with cross-compile set to the appropriate thing for your architecture, the right thing will magically happen. The right thing will magically not happen, because your upstream will not have done this for the GI tools, because they have only existed for 1 year and only in Debian. But like in principle, this is harmless for everyone else and helpful for us. And there are many other build systems, because lots of people look at all the build systems and think, this is all awful, I'm sure I can do better. Spoilers, they can't, but, but many have tried. And if there is another build system that we care about for cross-compilable packages, again, we don't know how that should be set up, but if it looks vaguely like Meson or vaguely like CMake or something, we can probably at least give useful advice. One of the things you might well want to do with GI is bootstrapping new architectures. So you have just, picture yourself, you have just invented like LungArch or RISC-V or something like that. You have no packages for this architecture, but you have a PC, and you have a cross toolchain and some sort of simulator that's very slow but works, maybe. And you want to start from scratch and get Build Essential and a minimal part of Debian so that you can build the rest. And in this scenario, which Helmut Groner has been the main person testing recently, you really don't want to rely on QEMU, because QEMU might not even know about your pet architecture yet. Or you might have written a branch of QEMU that does know about your pet architecture, but it's not got merged, and or isn't reliable, or is horrendously slow, or something. So, ideally we start small with this. We want to go all the way back to how do you cross-compile? Don't. And just turn this stuff off. And in practice, you can get enough of the lower level parts of GNOME to be useful without this stuff. So you could have a version of glib that you can use from your C programs, which is in the dependency chain of like Kerberos, I think. There's some really weird way that it gets into the bootstrapping set. And because you don't, we're assuming that you don't have a specimen of your architecture yet because it isn't finished. You're not going to run the tests either, so you can turn off a whole lot of test dependencies and skip that bit. And you don't need QEMU to emulate any of your stuff. Unfortunately, so I started on this cross-compiling GI work about a year ago, with some of the initial work on it being at the previous version of this very conference, and talking to Helmut Groner about what was required and what we ought to do. But unfortunately, since then, glib has absorbed some of the GI tools, which obviously they are part of a glib development environment, so we put them in the dependencies of the dev package. But it's the compiler for the host architecture, and oops, you can see the problem here. So recent work on this This is in the last, month, 2 months, something like that. glib has ended up with its main development package actually being a meta package. So there's basically nothing in there. There's like one script or something. It is usually still the right thing to build depend on. If you're building something high level like GNOME, you probably still want this. But if your package is way down the dependency stack and you need it to build like Kerberos or libcurl or something equally low level, avoid this. And instead we have, we ended up calling it libgio 2.0 dev. GIO is the highest level of the C libraries that are in glib, as it happens. We gave it that name so that we could split out even smaller packages for the lower level parts if we really need to. I'm very much hoping we don't need that because we don't want to have a giant proliferation of tiny packages. The main dev package has everything you might want. It's got all the tools, it's got all the developer tools, it's got all the tools that ends up on end user systems as well. But for the lower level bootstrapping friendly one, we didn't include those. There are recommends, but you'll usually have those turned off for bootstrapping anyway. So you might, if you need these, you do have to ask for them. We don't want to second guess what people are doing at that level. And another piece of work that has landed very recently at about the same time as this is we have this slight side quest, cross-exe wrapper, which is something I thought of while brainstorming how to do this stuff. So when I prototyped this, starting about a year ago, I was using QEMU directly because it works, it's good enough. But it's not really GI's job to know how to run an ARM binary or RISC-V binary or whatever you might be running. So we now have this package cross-exe wrapper, which Helmut Groner has added to the architecture properties package. And this contains a tool that is the architecture name dash cross-exe wrapper. And at the moment, this mostly still runs QEMU, but it has some special cases for particular pairs of architectures where there is something better we can do. So for example, for i386 binaries on x86-64, we just put a Linux 32 prefix on it to pretend to be 32-bit, and it's good enough. And if we find that there are cleverer, faster, more magic emulators for particular architectures in future, like we might want to use FEX instead of QEMU on ARM, we have the option of doing that, and we don't have to change it in every package. It can just be in this cross-exe wrapper. The name for this is heavily inspired by exe wrapper, which is a built-in build option in Meson. While designing their cross-interface, they put in this first-class citizen interface for how do you run a binary anyway. So this is for things like QEMU, but also Wine. If you're cross-compiling targeting Windows, you could tell Meson, I have this exe wrapper, it's Wine, it can run my Windows binary, and then Meson will happily run your test suite, and it will just prefix the right command to your tests, and hopefully they will work. I mean, they won't work because they're tests, they never work, but good start. And again, at the moment, this is something you have to do explicitly, but in the glorious future where all of this is automatic and part of the toolchain itself, maybe you won't have to specify that. Maybe it will just be if you have cross-exe wrapper installed, then it will automatically get passed to your Meson build by DebHelper. So this is all, everything I've talked about so far has been stuff that quite few people, mostly me, have been doing in the glib and GI packaging. But we're at the stage now where it's useful to fan out from there into the rest of the GNOME, GTK, GNOME adjacent ecosystem. So a very easy thing you can do in existing packages is if they contain GI XML, or if they contain type libs, you can give them this provides. And similarly, if they compile GAR XML during their build, you can give them this depends, and the deb helper tool will automatically expand these to the right thing. So this and it does this even for if you've bundled together several interfaces into one package, like a low level and a high level part. It will generate the canonical name of both of them, so that that structure is not actually like as hard coded. And if you use debhelper compat level 14, I believe you don't even have to explicitly add these, because it goes looking for every substvar that is something provides, puts them all in your provides, looks for every substvar that ends in :depends, puts them all in your depends. So if that works like I think it does, that will be really useful. So then if your dependencies have done this, you can build depend on exactly what you use. If you are using this interface, then machine translate it into the name of a package. Same principle as how we package shared libraries. The package name, whether it's a real package or a virtual package, is deterministically generated from the namespace you're importing. So your API is just a name, and names are APIs. And you will get build time warnings if you haven't done this. Sometimes you can just add it, and that's great. Sometimes you can't because your dependency hasn't done the previous slide yet. But if your dependency has not yet done that, it's a very easy patch to send to them, and then just wait for them to commit it. Going beyond that, if you want to be a bit more advanced, you can make it possible to cross-compile your package. And there is a README provided in the GObject-Introspection toolchain, which is also something you need anyway if you're doing this, which explains how to add the correct runes for your build system, ranging from autotools, mostly works automatically, through to Meson. You need to add some extra stuff right now. Hopefully you won't forever. And there is a bug open about you need similar things for one of the tools shipped with Valor. We have a prototype workaround for this. I tried this in libportal, which is a conveniently small glib-based library, but the workaround is kind of nasty. I have to generate a cross-file locally and hard-code knowledge about how Valor works. And there is a bug open against Valor saying, please make this easier. So if someone who actually knows Valor, which I don't, can review my contribution there, that would be great. More advanced than that, you can implement the NoGIR build profile, documented in the same README file. So you can have parts of your build just automatically fall off if the person building the package has said, I don't care about GI, just give me the minimal set, which is really good for bootstrapping particularly. And you can either do this with virtual packages and not need to go through the new queue, or you can do it the nice way by adding an entirely separate binary package, but then you will need the FTP team to review your stuff. And if you're making a new package, please just start from making a separate package for the GI. It's nicer. You're going through the new queue anyway. There's really no cost to that. And if you happen to be a build system maintainer, so my request here is AutoTools has these GNU tuple prefixed tools. The kernel has these GNU tuple prefixed tools. Just use them, please. It's a de facto standard, and yes, it makes your command lines really long, but it works. And in practice, if you're building an operating system, you're going to build at least one thing with AutoTools, so you need this to work anyway. But if you're not willing to do that, if you have something like Meson cross-files, it is good if you can centralize the choice of what tool you're using so that people making a distro only have to do this once. There's been a bug open against Meson for this for quite a long time, and I think I have reverse engineered what the maintainer wants. So there is now a pull request open that will make the cross-file that I described earlier, completely unnecessary. Yay. If that is actually correct and gets reviewed. Thank you. So, questions?
So thank you very much. That's marvellous. It's only been annoying for about 15 years now, so well done. But just to go back to the, what is it, so what you did with LDD obviously is the right thing to do. Stop doing that, pass the files instead.
Right.
What is it the dumper does that means we can't do that at the dumper level, or indeed make an object introspection multi-arch, like binutils multi-arch style, so just teach it to do more than one architecture? Is that actually unfeasible? Because it seems to me that would avoid the cross-exe, QEMU, whatever dependency thing, which is obviously a little bit.
So because the object system is fundamentally imperative code that happens during program initialization, we can't necessarily assume that it's identical on every architecture or on every distro anyway. So for the actual introspection step, we are going to have to run the dumper binary anyway. There's kind of no avoiding that. Like you could have a property whose default is different depending on what architecture you're running on, that's done programmatically. And the default value for a property is something that is part of your API, so it's something that ends up in the XML, so we want to be able to learn that. The use of LDD is just upstream is doing what looked like the easiest thing at the time to find the dependencies of your shared object. We can avoid that by just parsing the elf header, which is essentially what you said. It's a tiny, tiny subset of what binutils multi-arch does. I think that the program I wrote to do that is just completely generic. You load any elf binary on it. It doesn't even have to be from Linux. It could be Solaris or something. And it will find the library names and print them to standard out and be happy. But that's a really small part of what's being solved. It's not the hard part. And also it's something that should be reasonably easily upstreamable, so it's like a small step towards getting this more integrated.
Thank you very much, Simon.